All right, here we go. All right, guys, so let's start on, this is page 149 in the notes. I think it's like the second or third page. We kind of left off with the problem before it, the iodine 131 problem. We finished that. All right, so let's start here. So we're still doing decay right now. So this one says, fact, living things contain two kinds of carbon, carbon 12 and carbon 14. When a person dies, carbon 12 stays constant, so that doesn't change, but carbon 14 decays. So the minute you die, the amount of carbon 14 present starts to go down. In fact, carbon 14 is said to have a half-life of 5,730 years. So the amount of carbon in us, it takes 5,730 years for that amount to be cut in half. That's crazy. All right? Things change in the amount of, this change in the amount of carbon 14 makes it possible to calculate when the organism died. Guys, I'm pretty sure this is carbon dating. So this is what they use to find the age of things that have died. So example 4 says, find equations of decay. Traces of burned wood, along with ancient stone tools in an archaeological dig in Chile, were found to contain approximately 1.67% of the original amount of carbon 14. If the half-life of carbon 14 is 5,730 years, approximately when was the tree cut and burned? So they basically want us to find the age of this tree. All right, well guys, this is a decay problem, so we can use the formula from yesterday that says A of t will equal A sub 0 times e to the negative kt, right? Because we're decaying. All right, well guys, they told us what the half-life is. They told you the amount of time it takes for the amount of carbon, which is A sub 0, that's the amount of carbon. They didn't tell us the exact amount present, but we know A sub 0 represents that. They didn't tell us the rate at which it's decaying, but they told us the half-life. So I'm going to be able to find its decay rate by knowing the half-life is 5,730 years. That means you will have half of the original amount in 5,730 years. So we're going to use that to find K, to calculate the decay rate. Then we'll be able to predict the age of the item that has 1.6% of the original amount of carbon 14 left. So we can't even use this fact yet. First, we have to find the decay rate. So we're going to find K. All right, so let's do that. So if I use this, I know the end amount is going to be half of A sub 0 equals A sub 0 times e to the negative k. The time it takes to get half of that amount is 5,730 years. So plug that in for time. Now, guys, it doesn't really matter whether you use negative k or positive k. Just know that you're finding a decay rate. So you will be using a negative number in the formula, but when you talk about that rate, we talk about it as a positive number. All right, so first I'm going to divide out my A sub 0s. Because if I'm going to try to solve for k, I want to get the base of this exponential by itself. So now I have 0.5 equals e to the negative 5,730k. Well, here we are. Let's natural log both sides so we can start getting to that exponent. And then to find k, we'll divide both sides by negative 5,730. And we find out that k is, how long is it going to take me to do this on here? All right, now guys, do you see this e to the negative 4? That's scientific notation. So that's times 10 to the negative 4. So you got to move this decimal 4 spaces to the left. 1, 2, 3, 4. So it's actually 0.0001209680943, and that's your number. All right, so K is going to be 0.0001209 680,943. I just kept all of them. Again, I'd like to believe the book's going to give you a number to round it to. All right, now we can use that number. So now the problem, sorry, there's lots of flipping back and forth for me. So now the problem says this. The amount after time t will be equal to a sub 0, because they don't really tell you the original amount. We don't need to know it. Times e to the negative, because it should be a negative number, but when you talk about k, it's a positive. Okay. So now they've asked you to find the age of an item that has 1.647% of the original amount of carbon left. So now I need to find out the time, the age, if you will, of an item that has 0.0167% of a sub 0 left of the original amount. So guys, we're going to plug this in for the end amount, and we're going to solve for the time it took for that carbon to get to 1.67% of the original amount. So let me go to a blank page, because like I said, this is just too crowded. All right, so here we go. When will the end amount be 1.647 of a sub 0? All right, so our job is to solve this for t. So like always, if I'm going to solve for t, start getting the base of that exponential by itself, divide out your a sub zeros. That's why we don't need to know the original amount. They divide out regardless of how much it was. And you're left with 0.0167 equals e to the negative 0.000129680943t. And then natural log both sides. And then divide by negative 0.000, so on. Go ahead, who's got a hand?
I have a question.
Go ahead.
Where did you get the 0.0167?
The problem said that the item that they found had 1.67% of the original amount of carbon left. So we used 1.67%. 1.67% of a sub 0. You got to change this to a decimal. So 0.0167 of a sub 0 of the original amount of carbon. Okay? All right, now guys, I'm not unbelievably great with these graphing tables. I didn't learn with them, but I did find yesterday that when you're using your calculator, and this kind of maybe helps to keep things exact, as long as you don't clear your screen, like my answer for K is still stored, right? So now I can ask my calculator, at the end of the day, I'm taking the natural log of 0.0167 and I'm dividing it by K, that really big number that I had to keep writing down. You can just keep it stored in your calculator right there. Don't clear your screen. Take the natural log of 0.0167, close catapult. Let's divide it by, if you scroll up, see how this number gets highlighted? Hit enter, and it automatically copy and pastes it for you. So now I'm taking the natural log of 0.0167, and I'm dividing it by that number K that I keep having to write down. Hit enter, and it's negative 33,829. Now again, here's the thing though. Because that K was negative, it doesn't matter what you do. You know the age of this item is 33,829 years old, okay? And again, that just goes back to the whole, we speak about it as a positive, we use it as a negative, but the answer is, it's basically telling you 33,829 years ago. But the age of it, I would round to about 33,830 years. I'm gonna round it to a whole number. So it's approximately 33,830 years old. Okay? All right. All right, I'm going to try to do this one. I should have enough time, and then I'm going to have to stop here and leave the last page for tomorrow. Can I get a thumbs up if everybody home is okay? Everybody all right at home? All right, you guys okay? All right, again, like I said, the numbers ain't pretty, but the solving is always the same. You divide this away. You natural log both sides. You divide by K. It's very repetitive. All right, let's look at Newton's law of cooling.
The answer is the
The
natural log of
0.0167 divided by that K, that really ugly decimal.
Oh, that's it?
That's it. That gets you time. That gets you tape.
Right, okay.
Okay? All right, I don't want to copy this formula down wrong. All right, this one says Newton's law of cooling. The temperature U of a heated object at a given time T can be modeled by the following formula. Ready? It's not pretty. U of T, the temperature of your item that is being cooled after so much time is equal to capital T plus the quantity U sub 0 minus capital T to the times E to the KT. Now, K will be represented by a negative number. They don't say it in the formula because, again, at the end of the day, it doesn't matter. We know it's going to be a negative number in the sense that it's cooling, guys. The temperature is going down. All right, where T is the constant temp. So guys, think of that variable. It kind of is going to be the air temperature in the room that the object is cooling in. That's like your air temp, your room temperature. So it's the constant temp of the surrounding medium, right? Like the surrounding room, the surrounding air. U sub 0 is the initial temp of your object. So guys, your initial temp, that's the temperature that your object has been heated to. You're going to heat an object to a temperature, and then you're going to let it cool to see how fast that temperature cools. So your U sub 0 is your initial temp. It's the temp it was heated to. That's your U sub 0. So if they heat the object to 100 degrees, and then they let it cool in a room that was 50 degrees, U sub 0 is 100, capital T is 50. And K is the negative constant, and it represents your cooling rate. And since it's cooling, the temperature is going down, it's a decay problem. All right, ready? Here we go. So the first example, the only example, says an object is heated to 75 degrees. Guys, that's U sub 0. That's the temperature it was heated to. And is then allowed to cool in a room whose air temperature is 30 degrees. So that's capital T. All right? If the temperature of the object is 60 degrees after 5 minutes, when will its temperature be 50 degrees? Well, guys, hold the phone. We don't know the rate at which it's cooling. We don't know K, but they gave us enough information to find it. So before I can find when the temperature will be 50 degrees, I gotta use this information to find K. They told me the amount of time it takes for it to reach a specific temperature. So if I know that information, I can calculate K. So guys, let's plug everything we know into the formula. So U of T equals capital T. What is your surrounding air temperature? It was 30 degrees. That'll be 30, right? Capital T is 30. Plus U sub 0, what was the temperature of this object heating to? It was heated to 75 degrees. And then subtract capital T, that constant air temp is 30, times e to the k, we don't know, and T is what we plug in. All right, guys, so we're gonna use the fact that it takes 5 minutes for T for the temperature to reach 60 degrees. So we're gonna set this equal to 60 and plug in 5 for T, and we're gonna solve for K, the rate at which this is cooling. Let me just get myself a blank slate here so everybody can see what I'm writing. All right, so here we go. And we'll clean this up as we go. So we know it takes 5 minutes to reach 60 degrees. So let it equal 60 and let time equal 5. So then we're gonna get 30 plus, well guys, 75 minus 30, that's 45, times e to the k times 5, because time is 5 minutes here. And now our job is to solve this for K. What's this cooling rate? All right, first we're gonna subtract the 30 away. So we're gonna get 30 equals 45 times e to the 5K. Get the base of your exponential alone, so divide the 45 away. Guys, you can reduce this, you cannot reduce it, it doesn't really matter, we're gonna natural log it anyway. But if I divide both by 15, I get 2/3. And then I get e to the 5K. So to solve for K, to get it out of that exponent, let's natural log both sides. And then divide by 5, and then that will be K. So the natural log of 2/3 divided by 5. And we will end up with K equals negative 0.0810930216. And again, K should be a negative number because it's a cooling rate. The temperature is going down. Okay. Leave it on your screen, don't clear it. So now that I know K, guys, plug it into this formula, right? Plug it into your formula for K, but make sure that's 45 because we have a cleaner version of it now. So now we know U of T equals 30 plus 45 times e to the negative 0.0810930216T. So there's your formula that will work with this cooling object. Now they want to know, when will its temperature be 50 degrees? Now you can answer that question. So now you want to know how much time, T, is it going to take for the final temperature to be 50? So set your equation equal to 50 and solve for T. All right, I'm solving this for T. Let me just get my board clear so you can see what I'm writing. All right, I'm gonna minus my 30. I'm not erasing anything yet. Minusing 30, I get 20 equals 45 times e to the negative 0.0810930216T. Divide the 45 away, get the base of your exponential alone. They both divide by 5, so 4/9. It doesn't even matter if you reduce it. You're going to plug it into your calculator anyway. Natural log both sides so we can get T. And now all you have to do is take the natural log of 4/9 and divide it by that number, K, and you'll get T. And if you have it stored in your calculator, that's great. So the time will be approximately this answer. Take the natural log of 49, 4/9, and divide it by negative 0.081. So if I go to my calculator, again, take the natural log of 4 divided by 9, close catapult, divided by, if you up arrow, it highlights that number for you. Use it, it's right there. Hit enter, and now it's taking the natural log of 4/9 and dividing it by that K value that was stored. Hit enter, and guys, it's 10 minutes. It's 10 minutes, because again, it kept the exact value of K for us on our calculator. So it's 10 minutes even that we get. So it takes 10 minutes for this 75-degree object to cool to 50 degrees sitting in a room that is 30 degrees. All right, now the rest of the problem is graphing calculator. So I'm going to do it all over here. All right. Michael, can I get rid of this?
Yeah, I just need the right side still. Like with the UT, this 30 plus 45.
Okay. All right, so now the problem says, using a graphing utility, graph the relation found between the temperature and time. So guys, they want you to graph this equation. That's the relationship between temperature and time. So plug it into your calculator. Go to Y1. We're plugging in 30 plus 45 times e to the negative 0.081 093 0216, and you got to use X for T. All right, and hit enter. Now I'm going to go right to the window. Guys, the way this function works is time goes in, the temperature that it is cooling to comes out. Well, guys, so think about it. X is your temperature. So X is your time. So my window, I'm going to let X be 0, like 0 minutes, like I haven't even let it start cooling yet. And then we've already gotten to, what did we say? It took 10 minutes to get to a temperature of whatever degrees. Let's put an hour in. Let's put 60 minutes in as my X max. Counting by 1. My Y min, guys, it's cooling from 75 degrees, the temperature, and it's cooling to in a room that's 30 degrees. So I'll put 0 if it ever reaches 0 degrees, probably not. And then my max, guys, the max temperature it was heated to was 75. So let's go 80 as our max. And then hit graph. And there is the relationship between time and temperature. So as time goes on, the temperature is cooling. But guys, look, the temperature is kind of leveling off at some point. All right, so the next part is part, what is it? Part C, using a graphing utility, verify the results from part A. So guys, in part A, we had to find the time it took to reach 50 degrees. So go to your graphing calculator, go to Y equals, let Y2 be 50. We're going to find out how much time does it take for this temperature to become 50. Hit graph. So the time it takes for this temperature to hit 50 is that intersection point. So use the intersection feature, and let's find out where these two graphs intersect. So go to second, trace, and we want intersect, number 5. We've already learned the intersect feature. Move this little cursor butterfly guy closer to the intersection point. I'm on the first curve right now. That's good. Hit enter. The second curve, it's right near the intersection point on the second curve. Hit enter, and then it says guess. Do you want it to guess? Yeah, I do. And hit enter. And guys, look, when the temperature is 50, X will be 10 minutes. So we're verifying that we did the right math. All right, go to the next part. The next part says, using a graphing utility, determine the elapsed time before the object is 35. All right, guys, go to your graphing calculator, go to Y equals, take out the 50, let's put 35 in. How much time does it take for it to be 35 degrees? And we'll find that intersection point. So right there, right here is the time it takes for it to reach 35 degrees. Find the intersection of these two graphs. So second trace, hit number 5 for intersect. Just gonna move it a little bit closer to the intersection point. Yes, yes, and yes. And it takes about 27 minutes, about 27.09 minutes for this object to cool to 35 degrees. So that answer is about 27 minutes. And then last. The last question says, what do you notice about the temperature as time passes? Guys, look at the graph. As time goes on, the temperature drops pretty drastically, but then it starts to level off. Does anybody know what temperature it's starting to level off at? This was 35 degrees. So clearly it's leveling off at a temperature near 35 degrees. Anybody know what temperature it's leveling off at? What was the temperature of the room this thing is sitting in? 30 degrees. It's slowly gonna level off until it reaches that air temperature, that room temp that it's sitting in. So as time goes on, the temperature of your object is gonna get closer and closer and closer to its surrounding medium temp. In this problem, that air temp was 30 degrees in the room, and that's what's gonna happen to your object. All right, can I get a thumbs up? Are you guys okay? Yes, we're okay with the graphing calc? Is everybody at home okay? Everybody's good? All right. Guys, I did make a second homework. However, I don't think you're ready for it yet. I think a lot of the problems on the second homework, they deal with the logistic model, which is the last page of the notes. You guys can do whatever you want. It's not due for a couple of days. I think you should see tomorrow's notes before you try it. But you should be able to get the first day's homework done by now, okay? All right, let me take attendance real quick, and then you guys will be good to go.